First of all, let me introduce myself. My name is Vladimir Petrović. I'm with the School of Electrical Engineering at the University of Belgrade. And a quick remark before we start. I put slightly more text into the slides because we are running in this virtual mode. So just in case any technical issues or you can't hear me well, you can still follow the presentation as long as you can see. So let us start. Okay, a few words about motivation for this work. So agents, autonomy, and intelligence, or more precisely, autonomous and intelligent behavior of an agent lies in the very core of the AI field. These agents, often aiming to mimic humans, other living beings, and their capabilities, represent an object of scientific interest and research for decades. And at the same time, interactive computer games recorded astonishing increase in popularity during the years, and more importantly, placed itself as a powerful test bed for an agent to research and develop. So game agents, also called non-player characters, attracted attention not only as an inevitable part of enhancing computer gaming worlds, but at the same time as an important aspect of general agent research in academic community. Over the years, virtual game-like worlds begin to be seriously taken by the researchers across different branches of science, and their enormous potential is widely recognized. A large number of human users spend a rather serious amount of time playing or interacting in these computer-generated environments, with some reports showing that students spend up to 20 hours a week participating in these activities. So computer games and all other kinds of game-like virtual environments, such as multi-user virtual environments, for example, Second Life, Open Wonderland, or Dare, which was the first one, as I know, proved itself as a fruitful testing ground for various research directions across the field of artificial intelligence. So, namely, majority of computer games are, by their nature, interactive and agent-populated environments. And bearing in mind all the previously said, as well as the fact that these environments provide us not only with the real-world alternative, but also with certain advantages comparing to the real world, it is rather expected that they are used for extensive research, development, and testing of autonomous agents with different features and capabilities. In his seminal papers, Professor Laird even observed these interactive worlds and agents inhabiting them as a powerful tool for researching of human-like artificial intelligence. At the same time, computer gaming industry is highly focused on the player's perspective and the overall playability of the video games. So regarding this, development of agents technology is recognized as an essential ingredient for more engaging playing experience. Let us go to our simulation system. Simulation scenario in this work is developed from scratch by using a Unity game engine, Microsoft Visual Studio integrated development environment, and C# programming language. Unity is a well-known engine, widely recognized and used in gaming industry. In this particular research, we used Unity 2D because it's perfectly appropriate for demonstrating the core ideas behind the research, and it's less expensive than 3D. Core programming is done with Microsoft Visual Studio and C# language, and C# is a modern general purpose language, and it provides us with an excellent support for object-oriented approach and script writing and problem solving, which is essential for this sort of work. So in our simulated game-like environment, the agent or non-player character faces a challenge that represents one variation of a picking task. This kind of task is chosen because of its wide applicability, not only to the gaming worlds, but to the real-world scenarios as well. So illustrative examples are mobile robots executing some useful everyday tasks, for example, domestic robot performing a garbage collection in some area, or a mobile robot picking the balls from the tennis court, etc., etc. So in this particular case, one of the objectives was to develop an environment that will be more immersive for the human user or player or a potential spectator. Therefore, a gaming scenario is chosen rather than some real-world test. So in a developed game-like scenario, alien enemy satellites are spawned across the simulated space world with no aim to emulate the real physical properties of the space. And one should notice that these satellites are spawned at random positions in the game world. And we'll go back to this fact later. Our agent, in the form of a spaceship, has a mission to destroy them by simply colliding with them, while at the same time it must take care of a certain time and energy level constraints that will be elaborated later. And every time it destroys an enemy satellite, its score increases by 1 point, and the same kind of task is imposed to a group of human users as well. You can see the screenshot of our virtual environment below the text. So first thing that is performed when simulation starts is satellite spawning, and an algorithm that is developed especially for this purpose searches for collision-free locations and spawns a predefined number, in this case set to 30, of alien satellites at those locations. Spawning of satellites is done simultaneously, and it is important to notice that each time the new simulation starts, new random locations are generated and chosen. By introducing randomness into the location selection, we can more realistically emulate the real-world processes and consequently avoid the situation where agent or human user can exploit deliberately or accidentally predictability and immutability of the satellite positions in order to enhance its score and overall performance. This is of particular importance when comparing efficiency of the agent and humans. So upon the start of simulation, our agent begins its movement around the space. Agent wanders around the space. It has no sensorial information about the location of enemy satellites. It just knows that it should destroy the satellite if it runs into it. The agent is deliberately developed in such a way because we aimed for a minimalistic structure, relieved of any unnecessary computational and design expense, and at the same time, of course, this design was meant to have a satisfying level of performance in order to be compared with the test group of human user chosen for this research. So our spaceship has an energy level. And therefore, if it runs out of energy before simulation time is up, it will stop performing its task. In other words, it will fail. In that case, the score will automatically drop down to 0. In order to prevent this, a spaceship must be returned to its power base at some point in order to restore its energy. Initial value of energy level is 100 units. Every second outside the power base, energy level drops down for 4 units. And vice versa, when spaceship returns to its power base, energy level increases for 4 units every second while it is in there. For the agent, the red flag for returning to the power base is activated when energy level drops down to 35 units. At the same time, the red flag for leaving the power base is activated upon a full recharge. Now, one should notice that waiting until a full recharge is achieved is not always the most optimal solution. You should also notice that simulation cycle is limited by time, 60 seconds limit. So after the time is up, mission is aborted. And all the values mentioned so far in the text are chosen in order to enable efficient and at the same time immersive simulation. So basically, the agent's behavior cycle that we want to provide can be described in the following manner. Moving from the power base, wandering around the space and destroying satellites upon collision, returning to the power base when energy level becomes critical, restoring energy level, and starting a new behavior cycle. There are several methods that can enable this kind of behavior. In author's opinion, the best way is to build control structure based on decision trees or finite state machines, which are recognized during the years as dominant method. We apply the sort of hierarchical finite state machine, and more precisely, energy level of our agent is out of the highest priority. In order to track the performance, display at the top of the screen shows number of destroyed enemy satellites, scored points, elapsed time, and energy level of agent or human user. 50 simulation cycles are performed in order to have a better insight in the performance of the developed algorithm. And a number of simulation cycles were chosen carefully, especially regarding the group of human users. Small number of simulations would lead to unreliable and possibly false results. And on the other hand, number of simulation cycles cannot be too large either, because too many repetitions would cause the influence of the purely untrained phase of data to the overall results to be diminished. Table on this slide shows performance data of the agent, including a basic statistical analysis. And as it can be seen, our agent performance was rather constant, bearing in mind its constraints. Our control algorithm provided an expected behavior. It never failed as it was designed. And while individual scores during the simulation cycle vary, which is rather expected, bearing in mind agents' limited knowledge about the outer world and its lack of sensorial information. So for the comparison, we have done the same kind of simulation with the test group of human users. Those are previously untrained human users, and a human user can move the spaceship using the arrows on the keyboard. One should notice that the most important main parameters of the simulation are exactly the same with the agent and the human users, in order to provide a fair and objectively performed comparison. So alien satellites are spawned in the same manner, the agent and the human user travel with the same speed, etc., etc. The main difference is reflected in the fact that the human user doesn't have a defined trigger for returning to the power base and restoring the energy level. It is not safe from failing, and therefore a human user must behave intuitively and accordingly choose which refueling tactics will apply, and adapt the tactics if necessary. So at the table at the right side, you can see the obtained performance data regarding the group of untrained human users. During the simulations, human users differently coped with the imposed task. This resulted in the fact that they applied different strategies. Some they had more aggressive approach, resulting in a larger number of failures, while some had a more careful strategy aiming to reduce failures even at the cost of lower scores. And this was especially noticeable in the initial phases of the experiment. So as it can be seen, they all achieved better maximum value than the agent. However, the agent generally performed better than the human users, and this is mainly reflected in the number of fails, mean value, and standard deviation. Compared to the human's, agent scored slightly better mean value, and at the same time, its scores are clustered closer around the mean value, indicating a more constant performance, which can be very important in certain scenarios. And also one should notice that as the number of cycles increased, human users became better in performing the test. So some concluding remarks. This paper presented the realization of the efficient and inexpensive designing and controlling of the agent behavior in a simulated game-like scenario. Furthermore, agent is compared to the group of previously untrained human users. Our agent's performance was rather constant and successful, comparable and even overall better comparing to the group of humans. And with the further expansion in number of test people, it could be expected that some would even slightly outperform the agent. However, current experimentation results can serve as a decently strong indicator about the appropriate level of agents' performance and competitiveness. This can lead us to a conclusion that in this particular case, a carefully designed and tuned control algorithm implemented in agents' behavior successfully compensated a lack of sensorial information and complex AI. And this result is not only important from the aspect of computer games, but also from the aspect of real-world applications, where inexpensive yet reasonably efficient design can be an important part of the development process. Therefore, in some scenarios, an inexpensive design can represent a better choice over complex AI regarding all the parameters. And at the end, work presented in this paper represents just one fragment of a wider ongoing research, which will be presented in the future. So that would be all. Thank you for your attention, and I hope that we will meet face to face at the next year's conference. Thank you again.
Thank you, Vladimir, for this presentation. It looks like you had a lot of fun doing your research, right?
Yes. Of course.
Okay, I would ask the audience for if there are some questions. We should hurry up a little, but one short question. You said this is the part of wider ongoing research. Could you tell us a bit more about the aims and challenges of that research?
Yes, well, this is the initial phase of the system. So I'm building a larger system which is oriented toward the research in agent theory, and it should be a part of some future publications. So I cannot reveal too much.